Got a couple minutes here. I'll wait until 10 of exactly. Numbers go up and down really weird. 4 people in and then down to 2 and then back up. Yeah, and I'll wait a little bit. I got about a minute of time here, so we'll see how this goes. Wow, everyone came in and then everyone dropped out. That happened the last time too. Oh well, we'll see how it goes. What's happening here? Got sound. Play theme music in the background. Alright, so I'm gonna get started. See what's up with everyone here. See, I'll pop in and out on me here. Alright, so we're going to look at function algebra and how functions in themselves can work as operating things. Just hello, everyone. And so we kind of have to step back and think, what do functions do? What we've been kind of doing is having some domain and mapping results from the domain into a range. And the function was the rule to do the mapping. But these rules can work from moving things from domain to different ranges. And we want to have ways of dealing with these things kind of as collective units, I guess the best way to say. And this book actually has a really good way of thinking about this. And it comes with the idea, if you're traveling in a car at a certain speed, so if you're traveling at a velocity in a car and you see something, you're going to have a reaction time. And the distance you travel in that reaction time can be given by a function. So I see a ball roll out in the road and I'm going at a certain speed. And so the time for me to see and react has, light hits my eyes, my optic nerve sends a signal to my brain, the objects recognize what that symbol is, and they send a response out, and I'm going to want to apply the brakes. And the time it takes for all that signal processing to go is really, really dependent on the speed I'm going. But in that time, I will have traveled a distance. And we can have a formula for that distance. We can have, that I'm going to go 11 feet for every 3 seconds. And so I'll have some reaction distance covered, given how far away the object was I saw. And so this time that I see something to the time before I can hit the brakes is a function. And again, this is in the front of the chapter for chapter 5. Well, then I'm going to hit the brakes, and your car doesn't stop automatically. There's a braking time. From when I hit the brakes, the car slows down, I decelerate, and that is also a function. from the time I hit the brakes until I stop. And so it's 1 foot per 9 seconds squared. It would be a good way of doing braking times if I'm doing things in my, stopping distance is going to be in feet and my X is in times. And so these two functions can represent different calculations that happen. If you're traveling at a given rate, the time it takes you to react to something translates into a distance, right? And I don't know, do you ever, as you're driving or moving about on the highway, notice different reaction times, right? It's why you have different following distances. But these two things together would make a stopping time. From when I see something to the time it takes me to apply the brakes and stop, I can add the output of the two functions. And I get the total distance I will stop given my ability to react and brake. Well, this is the beginning of the idea of function algebra, because I can take whatever I have for r of x and add to it b of x. And I'm able to combine the two functions into one function that solves the problem in front of me. And I have two components from it. But those two components in the end make a nice quadratic that I can use to figure out my stopping distance or stopping times. And this is really the concept of what function algebra is going to be. Is a function is something that defines a rule for a given set of parameters. We can add, subtract, or multiply these rules together to create a new function that solves a larger problem for us. And so our goal here with function algebra is to combine our rules together to get these new rules. Right? These are two separate rules that define two different things. But in my model where the things come together, I have a new rule. And so that's what function algebra lets us do. Now, your book is going to use a notation for function algebra. It's slightly different than what I use. So I'm going to kind of do what the book's notation and kind of say how I would show it. So we're going to say we have a function f of x, which will have some value, and g of x has some value. And when we introduce functions, this was the name of the function, and this was the independent variable the function could take. And we found we can drop different things into these independent variables. Right, the independent variable. That's one of the things that's going to help us is we can drop different things into these functions if we need to change a variable. And so the book's going to start with function algebra. They're going to put in parentheses the function f plus the function of g on a given domain. They're sharing an independent variable, and they're going to say that's equal to the rule that is the function of f plus the rule that is the function of g. Sometimes if I do an example, I would do it without stating the independent variable, because the independent variables are given, and for this to work, we're going to have to put the same thing in here. But this is a better notation, is to have this stated like that. And so I will try to avoid this sloppier shorthand. But if I do it, I'm not saying anything different. And so our first function algebra we have is we can add two functions. And what that means is that the rules that make up the functions come together through addition. they also end up getting the same domains and the same domain restrictions. So if the two functions have different domain restrictions, their sum will have the combination of those domain restrictions. So I want to, well, let me show all the rules and then we'll do some function algebra, paying attention. So we can do subtraction, which takes the rule and subtracts the other rule from it. It works like our operations worked before, right? But now we get everything that's in the rules for these. All right, what's the other? We can multiply and make sure and when the book shows multiplication, they write the two letters side by side. They don't put the dot next to it. And that's the same as these two functions being multiplied. And we can divide, which we have already started to talk about because we were doing rational functions, which hinted at the idea of a larger functional division. And so these are the operators we can do with functions. In fact, because a function takes a domain and spits out an answer for each element in the domain, functional algebra can be done with any operation that works on a number. At the end of the day, f of x, because functions have passed the vertical line test, if I put one value of x in, I'm only going to get one answer. These become mathematically relevant things that we can do anything that has a mathematical operation with it. Well, let's look at some of these and make them work for us. So I'm going to make an f of x. So I'm going to have f of x is equal to 1 over x. Now, one of the things I want to keep track of here is my domain for this function. X exists in all real numbers, except x cannot equal 0, because that would be dividing by 0. Also, the range of f, well, we'll use our rules from rational functions, because this is a rational function. This has degree 0, this has degree 1, and so this is going to have a horizontal asymptote at y equals 0. And so the range of this function is going to tell me that f of x won't equal 0. It won't spit out a value of 0. And let's give another function here. Well, if g of x equals 1 over x minus 2. Again, the domain of acceptable x values, I can take every x value that's a real number in, except x cannot equal 2, because if I equal 2, I would be dividing by 0. And the range of this function, again, this is a constant 0-degree polynomial and a first-degree polynomial. So I'm going to have a horizontal asymptote at 0. And this function in particular can never equal 0. Now, some functions with horizontal asymptotes cross the line, right? We saw some that bumped up and crossed the line. But these in particular, anything 1 over x and 1 over x to the first degree, you're not going to see that it crossed the 0 line. All right, so what can we do with these two functions? Well, we can add them. So f plus g of x is equal to f of x plus g of x. So I have 1 x plus 1 over x minus 2. But this new function that comes out of this we'll have a domain restriction where x is an element of all real numbers, except x can't equal 0 or 2. Because if it had any of those values, we would get a division by 0, which is not defined for us. So when we're doing our function algebra, our domain restrictions carry from all the functions we're doing the algebra with. And so this carries its domain restrictions over. And if we wanted to, we could say this would be x minus 2 plus x over x squared minus 2x. Right? This denominator is different from this denominator, so I'm going to multiply this by x minus 2 over x minus 2. That's going to give me the leading x minus 2. And this denominator needs an x to get the common denominator, so I'm going to multiply this by x over x, which will give me x. And when I multiply the bottoms together, I get x squared minus 2x. And let's see, I have 2x's up there. All right. So I have 2x minus 2 over x squared minus 2x. All right. And that's our new function. Okay, well, we can also do function subtraction and function multiplication and function division. And they all change the function noticeably. Let's look at the domain restrictions that possibly come out of some of these. So let's see here. Yeah, I'm going to look at one that has some domain restrictions slightly differently. Okay, I'm going to scroll up out of the blue here, and we're going to look at the function algebra that we can get when we have f of x is equal to 2 plus the square root of x minus 1, and g of x is equal to x squared minus 4. So the first thing we want to do is find the domains. The domain is the first thing that you want to do when you look at your function algebra. So the domain of f has this restriction. X minus 1 has to be greater than or equal to 0, or x has to be greater than or equal to 1. So the domain of f is x is an element of all real numbers, and x is greater than or equal to 1. And g, its domain, has no restrictions, so g can accept all real numbers. All right, let's do some function algebra and see what might come out of these. So the first algebra we can do is we can do f plus g, which will be f of x plus g of x. So 2 plus the square root of x minus 1 plus x squared minus 4. Well, we'll collect like terms. There's not too much like for like here. But the 2 and the 4 can come together, giving me a minus 2 on it. Now there's some neat things we can do with this. This new function, f plus g of x, I can find its value. Since x had to be greater than or equal to 1, let's find its value at that boundary of 1. So I could put 1 into this new function. I would get 1 squared plus 1 minus 1 minus 2. Or I get, that's going to zero out, and so I get 1 minus 2, or negative 1. Or, sorry, I'm trying to scroll to the right space here, which would be right there. I can put 1 into f of x, and 1 into g of x. I could put f of 1 and g of 1. So let's do that here. I'll say f of 1 plus g of 1. Well, f of 1 is 2 plus 1 minus 1, or 2. That's f of 1. And g of 1 is 1 squared minus 4, or negative 3. Right? I'm looking at the two parts on their own. Well, if I bring the numbers together, 2 plus minus 3, 2 plus negative 3, equals negative 1. One of the keys of function algebra is the algebra that pulls the function together should give you the same values as if you did the parts separately and put their answers together. Let's continue to work with these two functions here. So we're going to continue to look at 2 plus square root of x minus 1. G of x equals x squared minus 4. Oh, and the domain of this new function, because this restriction has to be met and this has no restriction, the domain of this new function, the domain of the sum, the domain of f plus g, is x exists in all real numbers and x has to be greater than or equal to 1. Because you can't break any of the domain restrictions of its parts. All right, well, let's look at a division. So we'll take f of x. Oops. We'll take f divided by g of x. And so that's the same as f of x divided by g of x. Now we're going to get the things that we get from polynomial functions in here. We're going to g of x, we're not polynomial rational functions. G of x can't equal 0, right? I still can't divide by 0, so I'm picking up an extra domain restriction. And you're going to find the thing that we're going to talk about a lot with function algebra and that we're going to keep coming back to is how the domain creates the range and how any domain restrictions propagate through. The things we're moving towards these exponential functions and how to reverse them, we're really focusing on how all the mathematics we did before, we take some input number and we get some output number. And we have to look at how those rules interact. And there's a lot of focus in function algebra out of the domain restrictions and those domain mappings to range. So f of x gave the domain restriction that x was in all real numbers and x had to be greater than or equal to 1. Now, this new function says is going to have a domain restriction where g of x can't equal 0, and g of x was x squared minus 4. Right? Sorry, I'm still using these two up here. X squared minus 4 and 2 plus the square root of x minus 1. So I need to solve this. So x squared can't equal 4, or x can't equal plus or minus 2. And so my new domain of my new function of f divided by g, my new domain, I start with all real numbers, but I have a restriction that x can't be plus or minus 2. Well, it already has the restriction that it has to be greater than or equal to 1. So I don't have to worry about the minus 2. I only have to worry about the positive 2, right? X has to be greater than or equal to 1 and not equal to 2. Or if we remember our notation, the interval notation, right, we could write this way. I have to be 1 up to 2. I don't exist at 2 up to infinity. These are the two notations that we can write to talk about our domain restrictions. But by combining these two functions, I get a more restrictive domain. There are certain values of x, if I input them, I'm either going to divide by 0 or I'm going to try to be taking a square root of a negative number, which means that they can't map back to a range. And so I have to limit myself to not taking those values. It's really, I find it, having done, and these things actually apply in the physical sciences very much. We have this problem where we have things that might be infinitely dense, or divide by zero, or getting infinite density, or things that happen in our physical models. And this idea of where our domain restrictions are actually becomes really important. And understanding how they come up from the different functions we put together tells us something about how our models are interacting and what values we're allowed to use. And so paying attention to them through here, I know right now it seems like a lot of niddly work, but it pays off. It really starts. We can start talking about regions where the function does different behaviors. If you if you look at the functions we're doing for the rational functions, and if you look at the functions we're going to be doing here, if you graph some of these functions in Desmos, you will see regions that appear where the functions do certain behaviors, and that pattern of regions is really defined by the domain restrictions. And so keeping them together will help us figure out where things are working. It also kind of tells you where the rules break down or where the rules change. All right, so if I want to do this division, then I would write my f of x up top. So what did we say we're doing? F of g of x. And so my f of x was 2 plus the square root of x minus 1 all over x squared minus 4. And that's the best I can write this in. There's no simplification coming through on this, but I have a rule and I have how my domains are working their way through. This is very useful. We can combine rules, and I think I'm actually going to go right to an example of this, and then I'll go into the next step of the next useful thing. And I like this example because it's completely alien from me and what I normally do. Right? I'm the science guy. I do stars and gravity and physical systems, and they have these physical laws. But I think one of the best examples of how functions can come together happens a lot in business, where we'll have a cost function. Which will make C of X, which is the cost to manufacture a product per unit, and the unit will be X. Okay. So I'm building something, and it costs me X amount of dollars per unit, plus maybe an overhead cost. So let's say there's a factory making pencils, and the factory's monthly bills or yearly bills, whatever time period we're going to analyze it from. So we'll say yearly bills is $12,000. Or monthly bill is $12,000. Electric costs, overhead products, or 12,000 units. 12,000 is small for that. That's these will, let's say we'll make pencils, and these are specialty pencils, right? Which you get your own thing on. So the specialty pencils, there's a base cost of the pencils, which is, and I'll use $1,200. Right, so you need to order so many of them, and it's $1,200 worth of pencils. But then the label you put on it costs man hours, and so there's $5 per unit. Why am I saying specialty pencils? I just needed it to be something. Should do what they do in business school when it doesn't matter what the thing is, and they call it the widget, right? Widgets, right? Because they don't match it. And so I can make a cost function where the cost is $5 per widget plus the base material cost. Or the base running the factory, but whatever the, right? So it's $5 in parts and labor per thing I make, and then I need to spend $1,200 for the utility bills or whatever that keep the factory running during that day of manufacture, right? And so this is the overhead or fixed cost, and this is the production cost. Right? The more you produce, the more cost it's going to be, and the fixed overhead is something that you have to maintain, and usually that's bills. Well, then I want to go sell this, and I get a revenue function. Now, revenue functions can be complex. I could be selling these widgets, and I could be selling them at $20 a widget, right? But I might have to advertise 50 cents a widget. There might be some advertising fee that goes into play that would complicate this. And they might not all be linear in X. They might be supply and demand curves, might not be flat lines. And so if I produce too much, there might be a quadratic term with a maximum. But what happens is these two things are separate things, right? The factory works on the cost production of it. The factory works on making sure that they can manufacture the product as cheaply as possible and as efficiently as possible. And then the marketing team works on finding a way to get the revenue to be the most per widget, no matter what other costs might come here. But the profit is your revenue minus your cost. And so by using function algebra to keep track of things, you can really have specialization where one division works on making the costs as low as possible, and another division works on selling as much as possible for as much as a profit. And you can separate those two equations. You can work on tweaking them. You can change the values. But then when you need to find your full value, you can say, well, I have 20x is my revenue, and I'm subtracting from it, and I'll put it in parentheses. Whoops, minus 1,200. And you now have your profit function. And so you can compartmentalize the things that make up the model coming through. And all function algebra is based off this idea that these things that are driving our equations, these things that we're measuring, or the things that we're looking for this output from, can come from different sources. And those sources might specialize in them. So that's why you don't... I also find one of the things people say with word problems is that, well, what goes into certain parts of the word problem? Well, if you can break pieces of the problem into self-contained units, you can kind of look at them as functions and bring your functions together. I think function algebra is a thing that's very useful just in thinking about things in parts. Well, there's another thing functions can do. And I'm going to go to the domain notation here. So this is some domain D. And this is a function, I'm going to say, this is going to be a function F. And it moves into a new domain, and we're going to call that domain E. And somewhere else, over here, I'll put this a capital F. We have some other function, G, that moves between these domains. And I'm going to give a very specific example for this, and it's an example I kind of thought of earlier as I was thinking about it, and I like it because it really separates these ideas of how we generate functions. Remember, we're looking for patterns in the real world that we want to turn into mathematical rules so we can predict the future. And we want to do this in a way that's beneficial to us. And so, one that's on my mind right now is, let's say this is the oil markets. And so D is the amount of money that I invest, and the amount of money I invest, and the function turns it into barrels of oil. Right? So I have some money. Based on the oil markets, that money will buy me so much oil. And I kind of want to predict what that'll be at different points in times. This can be a very complex market function. Right? The supply chains of oil, and oddly enough, it's in the news recently because we're producing more oil than we're using, and the supply chains have finally backed up that there's no place for the production oil to go. And we had a couple days where oil was negative money. They were actually paying to get rid of the oil so that the supply chain could keep flowing. And this happens in supply chains. This function F here is complicated, because it deals with every populated country in the world's oil production and oil use, and it drives the price. So working on this function alone, right, is entire people's careers. But getting barrels of oil, well, I've never bought a barrel of oil. I've never went out to the store, bought a barrel of oil, and then said, I've got to turn it into gasoline so that I can drive down to the mountain when I'm allowed to again, and then dance and get chalk all over me in front of everyone. So these barrels of oil don't mean much to me, but gallons of gasoline do. And so this could be the refineries, right? And so the refineries have a process where they can take and I'll even say it's the cost of a gallon of gas, right? Their process, they can take barrels of oil and they kind of boil it down into kerosene, number 2 heating oil, and gallons of gasoline that we have in the car, diesel oil, right? There's different levels of product that are made out of those crude barrels of oil. And that process is very complex. There are people who spend their whole careers doing that, and the functions that drive G for the efficiency of making barrels of oil into gallons of gas are extremely complex. Now, there are nations and companies that need to start here and get the answer there. They need to blend all of these inputs and outputs to predict what they're going to do. But if they need to change road taxes, if they need to ease restrictions or increase restrictions on certain market forces to make sure that their populace has the energy needs that come from burning this particular fossil fuel and the whole process on it. Now, these people shouldn't have to learn everything about function F and everything about function G. Right? That would be actually asking for someone to specialize in something that people spend their whole life specializing in twice, right? You're going to become a specialist in 2 distinctly separate fields: market economics of supply and demand of barrel of oil, and the physical efficiency of turning crude oil into petroleum products. Right? So 2 separate things, 2 distinct skill sets, but the people managing it need to combine those. And so what would be really, really nice is if I could get the input into my G function to be the output of my F function. And we have a symbol for that. It's an open O. It's called a composition or composite function. And this reads G composed of f. So this is a composite function. And it is equal to, and I will use the book notation again. Do not like these extra parentheses they put in, and I always forget them. G composed of f of x is equal to whatever my function g is, and I put into it the output of function x, or f. So I can start with domain D here. I drop it into domain F. It spills out an answer, and that pops into G and gives me domain F here. And so I can move through all of these. Well, there is a way that I could use this to make a new function that takes me from D to F directly. And that's what a composite does. So let's look at a composite function here, and then we'll move into some of the things about the domains. Yeah, I'll use the one the book has. So we'll say let f of x equal x squared plus 3x plus 2. Right, this has no domain restrictions. Right? And g of x equals 1 over x. And I'm going to make the domain composition of f composed of the g function. Which is saying, for my f function, I drop in the output of my g function. So the first thing I do when I have any type of function algebra is I look at my domain restrictions. This has no domain restriction. It's a polynomial that's free. So anything that pops out of g is good, or because nothing is going to restrict f. But g has the domain restriction. Right? X can be all real numbers except x can equal 0. So my new function will have a domain where x can equal 0. And that's the only limiting thing on this version of the function. All right, but what does it mean to drop this whole thing in? When we had a function, if I did f of 3, I would put in parentheses the 3 everywhere I saw the x. Right? That box of the function let me drop in whatever was in the parentheses into where the x is. And the same thing happens here. G of x, oh, I have an equal sign here. G of x is equal to this rule, 1 over x. So I can drop in g of x is the same as f of 1 over x. I'm going to drop in 1 over x wherever I see x. So I get 1 over x. Well, that's squared, right? Dropping in a 1 over x into this x, plus 3 times 1 over x plus 2. And if you've heard me say keep your parentheses for functions so that we can look at it as a barrel, it'll help you keep track of your signs. Well, it also comes in very useful when we're doing this, because the ability to drop a whole thing into our function. And to be honest, with the difference equation, we were doing some of this already, because we were doing, the x minus the h, or x plus h. You can do either way, but you get x plus that h value in the difference equation. And here we have and we drop the x plus h into everywhere we saw x, and we gather all the like terms and try to get our h's to cancel out. And here we have everything that's in g of x falling into the x. And this will give us 1 over x squared plus 3 over x plus 2. And we have our new composite function. We have everything from that the rule of G would be doing to what I put into my domain, filtering through G and into F. But we can write it in one form. We don't have to do it in two steps. Right? And so composites functions, if we think back to this idea, really help us map between disparate concepts. We can work on getting one part of the problem right and then spill the answer into the next part of the problem. We can specialize. I do think of composite functions as the beginning of specialization in functions. All right, so the domain of the composite of two functions can be tricky sometimes. You really need, I will write the domain down on every step. Sometimes you don't want to simplify right away. And I'm actually going to use the example the book uses here because this is kind of a good idea about this. And it's going to come in handy when we look at inverses. So I'm going to have these two functions. Okay? Now, if I compose f composed of g, that means I'm going to, wherever I see x, I'm going to replace it with g. Well, if I square this, the square cancels out the square root, and I get x minus 1. Now, if I look at that result, there is no domain restrictions on it, right? And it might be hinting, I'm free to put in whatever I want in here. And if you've noticed, when I've been doing these function algebras, the first thing I say to myself is, well, what is the domain restrictions for this? And so the domain of f, well, that's a polynomial, right? What are our two things for restrictions? We can't divide by 0, and we can't take a square root of something that's negative. Well, for f, there are no domain restrictions, and so we get all real numbers. For g, well, this is a square root. So x minus 1 has to be greater than or equal to 0, or x has to be greater than 1. And so for the domain of g, x is all real numbers as long as x is greater than or equal to 1. My composite function, because my input is initially coming through g, my composite function gets that domain restriction. This new composite function cannot have values less than 1. I will stress it now. It takes time. It's extra paperwork, and I think we all hate that. We want to get to the answers as soon as possible. The stuff we're doing is starting to take up a couple pages, or page-ish, right? We have to keep track of things. We're doing a lot of bookkeeping and keeping track of things. In everything with function algebra, keeping track of where you are in your domain is key. Every function that you're going to use, you should have an idea of what its domain and domain restrictions are. Then when you go to use it or apply it, you should look if you gain any more domain restrictions on it. Composition of functions come in handy for what we're going to begin next part with. And we're gonna look at one last thing here, which is inverse operations and inverse functions. And I'm gonna take a road trip back to our friend PEMDAS or PEMDAS or however we want to remember this. So I have parentheses, grouping symbols. I have exponents and their roots. I have multiplication and division. I have addition and subtraction. And our game with mathematics was if I had an operation, I wanted to be able to invert it. So if I had 5 plus 3, or plus 2, since I wrote it wrong, equals 7, I want an inversion that says 7 minus 2 equals 5. I want some operation and its inverse that lets me go backwards. Right? When we're doing it, all of these properties of real numbers, I said if you start on the left hand side and you go to the right hand side, you should be able to start on the right hand side and go to the left hand side. Anything we do, we should be able to undo. And that's what inverse operations are. We move our steps backwards. And we want to find our way back to where we begin. So we could say, I start with 5. I end with 7. Here I start with 7. And I end with 5. I end with horrible handwriting. I will say writing on this is much harder than a blackboard. It's 10 by 7, so it's like writing on a paper. It's much smaller motions, and I think plus I write my lecture notes out, so I'm writing a lot now. Writing about 2 times as much, and I think this is the beginning of immense hand fatigue. Is my scribbles coming through? I really want this camera to come in. I've had a camera order canceled now due to bad shipping. Because I have a blackboard and I want to play the blackboard, but my webcam just doesn't focus in well on things like that. So I'm trying to get a camera for that. And I can't get my phone hooked up to the stream. All types of technical problems, right? But I want to write a little bit bigger. All right, but the idea is we start with 5, end with 7. Here we start with 7, we end with 5. Well, that sounds familiar, right? If I have my 2 sets of numbers, and I have some function, and if I start with A and end with B, or I start with C and I end with D, it would be nice if I could define something that starts with B and ends with A, and starts with D and ends with C. If I can invert operations I do, wouldn't it be nice if I could invert functions? And so if these rules are the function f, then in the backwards process, we're going to call the inverse of f. And it's written with f with a -1 up above. We talk about going forward and backwards. We take some mapping and we reverse the rules to it. And so this is an inverse function. Not all functions can have inverses, and we will look into that. And it has to do with the requirement of a function. For each input value, you need 1 output value. And there are some functions we have that land in the same spot. And so we're going to look for those. But let's play with how we're going to invert a function first. And work on what we can do with inverse functions. Actually, I want to start with the problem child. I've put the problem child up a couple times today, and I've said, hey, we're going to look at this thing a little bit later. And here's our problem. If f of x equals x squared, I have a mapping that will map back to, I'll just give one example here. Right, here's my D domain. If I map +1 or -1, and I map them to their range, so that's my D domain and that's my range, well, +1 squared is +1 over here, and -1 squared is also +1. These 2 points in a valid function come over to 1 point. That means if I try to reverse this, if I'm sitting at +1, Which way do I go backwards? Right? I can't make a decision arbitrarily. And so this function isn't one-to-one. So f of x squared is not 1-to-1. My domain has to map one point here goes to one point over here, right? These don't go to two different areas. And we saw this as the vertical line test. X squared passes the vertical line test. But this part here going back, well, it's failing the horizontal line test. And so if you don't mind, I'm going to try to pull this up on the graph here. So if we look at the function x squared, and we get its graph here, any value of x gives me one and only one answer. And that we call the vertical line test. And functions had to pass the vertical line test. If I put in one number, I can only get one number back. But it fails the horizontal line test. In fact, any number and its opposite will yield the same result. Right? And so it fails the horizontal line test, which means this isn't one-to-one. And so I can't actually make an inverse of this unless I do something to make this one-to-one. And the general thing we'll do when we need to invert something that's like this is we'll have to say, well, you know what? I'm only going to talk about the positive values, which we tend to do when we're taking square roots of numbers. We say, well, we only want the positive answers. Or we can do the opposite. We can say we can talk about the negative answers. And so we'll usually enforce a domain restriction where we'll say, I only want the positive values of x. And now I have something that I can do one-to-one with. So if we need to create an inverse, we need this one-to-one nature. And we sometimes might need to enforce a domain restriction to make it happen. I'm going to plot a special line up here, y equals x. I'm going to make it dotted because it's a very important one here. And I'm going to make it purple. And I'm going to show the inverse to the positive values of x squared. And so the inverse is going to be the square root of x. And I want to make that green so it stands out from. And we should notice something about the inverse. It looks very similar to our original function. The job of the inverse is to take what was the range of one function and make it the domain of the new function. And what was the original domain becomes the range of the inverse. We're swapping the domain and the ranges. We're switching things around. We're mirroring them. And if y is the range and x is the domain, if y is the range and x is the domain, this line y equals x is what these functions will make a mirror out of. So see how they mirror graphically? Does not look like this is saying much, but this has solved so many mathematical problems. We have created functions that we will not have a symbol we can do something with. And I'm going to switch over to the blackboard here. And I'm going to show you where this is going and why this next section on inverses and inverting functions are really important, and why the graphical representation is really, really important, and why we spend some time on this. How do I solve for what's up there? I have no mathematical operation that gets things down from exponents. Well, it'd be nice if I could find an inversion for it. And so what we're going to do is we're going to invent the rules of inversion so we can come back to this and we can invent the mathematical rule to bring things down from the exponent. So I can't divide, I can't take roots, can't take the xth root if I don't know what x is. And so we have to work on how am I going to invert this function of 2 to the x. And so to do that, we're going to focus on what inverting means. So if I am taking a map of a function and I'm having it go backwards and forwards, let's use the book's definition. We're going to use a one-to-one function that we can invert. They become invertible. And that says that if there's a function f that has elements C and D in its domain, and they are not equal to each other. So if I have two values in my function, two separate x values, then the y value for C cannot equal the y value for D. And that makes a one-to-one function. And it's saying that for every value there is a unique answer from the function, and that answer only maps back to 1. And I think visually that horizontal line test is the best way of saying it. Well, if we have a one-to-one function, we can make its inverse. And I want to show you the rules for the inverse. So the first thing we do is step 1. We let f of x equal y. We're going to change a variable here. Then, because y represents the range and x represents the domain, we're going to say we're going to flip the domain and range. We're going to change all y's to x's and change all x's to y's. So we flip the domain and range by doing that. Solve for y. And then we're going to let y equal the inverse of our function. And so these are the 4 steps we have to do to make an inverse. Well, it can be a bit odd. So let's look at a couple of these here. And let's try to find some nice little tricks that come out of them. All right. I'll get that on the screen here. And so I'm going to write my f of x over here. F of x equals negative 7x plus 2. So if this is my rule that's taking some domain and mapping it to a new range, and I want to reverse that rule, all right, well, I'm going to use these steps. So step 1, I want to let f of x equal y. So I've just written it in a new form. I've changed my variable. Now I'm going to change all y's to x's, so this becomes x, and all x's to y's. It's weird. It bugs people, just swapping your variables around. But I want you to understand what we're doing is we're swapping the range and the domain around. And that's what we need to do for an inverse. Now I'm going to solve for y. So I'm going to add 7y to both sides to get rid of the negative sign. And then subtract x for both sides. And then divide by 7. And that's my inverse. Well, let's graph this and see what it looks like. So let's switch back to the graph. Now I'm going to keep this y equals x midline, because that midline is really good for defining the mirroring point that we want to do. So negative 7x plus 2. Now when I did the inverse of that, I got negative x plus 2 divided by 7. Make sure you guys are still on the graph there. And let's say that louder. I got negative x plus 2 divided by 7. Notice, here's my original function in blue. Here's my inverse in green. And notice how they mirror the line y equals x. They're mirror images of each other. That's what it means when we swap the domain and range. We have a way now of reversing everything we did in our functions. All right, well, let's switch back to the blackboard. Let's look at a complicated one that's a little bit tricky until we work with it a few times. Let me see, where did I put it? There we go. So I have some function equals 2x plus 1 over x minus 1. Guess I want to keep in mind that the domain of f, cannot exist in all real numbers, but x cannot equal 1. And its range of f, well, my range of f, if I look at my rational function rule, they have the same x, and so this is going to approach 2. So there is a chance that f of x can't equal 2. And I'm going to try to confirm that. Well, a nice way to confirm that is you'll see in the inverse. So let's watch what happens here. Because our inverse is we're going to switch our domain and range. And our inverse is going to tell us if there's any restrictions on the range also. So let's use our rule for inverses. So I'm going to change f of x to equal y. And I'm going to replace all y's with x's and all x's with y's. And now I want to solve for y. So I'm going to cross multiply. I'm going to get x times y minus 1 is equal to 2y plus 1. I'm going to distribute. xy minus x equals 2y plus 1. I'm going to bring this up here. And I'm going to get my y's together. Let me rewrite what I have over here. X equals 2y plus 1. I'm going to move all my y's to the left-hand side. So I'm going to get xy minus 2y. And I'm going to move this x over to the right-hand side, so I get x plus 1. Now, both of these have a y in them, so I'm going to factor out a y. And then I'm going to divide by the x minus 2. And so we're going to look at this and we're going to say, hey, guess what? This is my inverse function over x minus 2. And this inverse function, so the domain of x minus 1, has a restriction where x can't equal 2. Well, that's kind of what I thought when I looked at my horizontal asymptote rule, right? There's a horizontal asymptote coming on. There was a chance that x couldn't equal 2. It depended on if it crossed back or not. But the inverse is telling me, yeah, I can't equal 2. And so now we know something about the range here. And the range of my inverse function, well, that's the domain of my original function. It's not going to be able to equal 1 no matter what we do. And so the idea of inverting a function is swapping the domain and the range. Swapping the domain and the range. Because if the domain is what you start with, and the range is what you end up with, if you flip those around, you're starting at your end point and you're ending at your beginning, which is what we want to do. We want to reverse the process that we're doing. All right, there's one thing that will prove something is an inverse. If I compose my function of its inverse, I'll get x. And if I compose my inverse of my function, I'll get x. If both of these are true, this is a one-to-one inverse. Okay, this is one-to-one. I'm going to say it again. This is one-to-one, since my hand is definitely not making those ends work out right. I wonder if I can get a bigger tablet so I can write a little bit bigger. All right, so the last thing I'm going to do here is use this test to test if something is an inverse. That'll be the last thing we'll do here, is this test coming across. Here. All right, Blackboard check. So I keep double checking the Blackboard. I don't want to lose it here on this last one. All right, so we're going to take a definite one-to-one function and we're going to verify it is. All right, so where I want to find a good one-to-one function that's a little odd looking. Give me a second here. I have like 5 papers I've been going through between the 2 courses and I have 2 sections. I think I'll use this one here. So if I have a function f of x equals x plus 2 divided by 9, and I'm going to state that its inverse is 9x minus 2. All right, to prove that this is true, the composition of f and its inverse should equal x. So we'll put a question mark over that. And the composition of f inverse from the function should also equal x. And so I'm going to put a question mark over that. These are going to be the tests I'm going to do. So I'm going to compose f of its inverse. So I'm going to drop into the function f its inverse. So what that looks like is, here's f. Wherever I see x, I replace it with all of this. So 9x minus 2 plus 2 over 9. Now I can remove the parentheses. The 2's cancel. And I get x. So it passes this first check. So that passes that. So I'll put a check mark on because it passes now. All right, let's do this other check. The inverse composed of the function should also equal x. Well, this is the inverse, so inside of the inverse, I want to put in f of x. Well, that equals, well, here's the inverse, 9x minus 2. So wherever x is, I want to put in f of x. So 9 times x plus 2 over 9 minus 2. When I do this multiplication, those are going to cancel, leaving me x plus 2 minus 2. The 2's cancel out, and I get x. And so it passes that check. And that's what we mean that when you put an inverse into its function and the function into its inverse, you get x back. The rules cancel each other out because they're supposed to. They're supposed to be doing the opposites of each other. And if you do the two opposite things, you don't go anywhere. And that's how we check for inverses. All right, that takes us up through inverses. Inverses are important things that we're going to need to use. I'm going to start back up next Thursday. We're going to review a little bit of inverses, and then we're going to start using them to help us solve this problem of things that we don't have a mathematical reverse to. Right? Multiplication and division, we have that inverse. Exponents and their roots, we have that inverse. Addition and subtraction, we have that inverse. Exponentials, which we're going to define, we're going to have to figure out how to make their inverses also. And it's using these rules that are going to let us do this. Using this idea that swapping the domain and range let us do things. So that's all I have for this evening. Thank you. Sorry for a couple little technical hiccups there on that blackboard. I will try to do, and I endeavor to do better. All right, everyone, you have a good evening. Email me questions. Eric, exams are going up tonight. I just took them this afternoon. I'm comfortable with them. I have them trimmed down. So the exam for Chapter 4 and the final exam will be up tonight. I'm publishing it right now as soon as I'm done here.